Today I choose the topic simulation based transient response of RC series circuit for this video session. Now, before we start simulation based approach, first you have to know what is transient. Transient means sudden change. Okay, sudden change in any circuit. So when you can see here, there is one voltage source. Now one switch is there. So if I close this switch suddenly, initially across XY, no voltage is coming. So we are getting zero voltage. But whenever this switch is closed very quickly at t equals to 0, then there is a sudden change of stable voltage. Say initially it was 0 voltage, now it will jump to V into UT voltage. If V is your 5 volt, then we can say from 0 volt to 5 volt jump, and the jump is very sharp, and this sharpness depends on this time that switch, that how quickly we can close this switch or open this switch. So this is called as the transient or switching occurs from lower voltage to higher voltage. So we can say this is a positive transient. Now after that, again if I open the switch, then we will find from jumping or switching from higher voltage to lower voltage, and that transient is called negative transient. Now in this circuit you can see there are some R, L, and another R is also there. Now for this case, what will happen, that one initially one current source was connected but switch was closed. Okay, but suddenly when this switch getting open, that time one transient occur, means one switching occurs from one level to another level, and because of this change, some parameter or some discrete component like inductor, some element inductor, capacitor can't follow that sudden change. Resistance can follow that sudden change, but inductor and capacitor, because of its inherent property, it can't follow that sudden change, and it takes some time to follow that sudden change. And because of that, as it is taking some time, so we will find at the response time, the response curve, there is a lag, and that lag we represent using a transient response. Now here you can see that if we connect voltage source without switch, say the voltage is constant, there is no switching from one state to another state. So this condition you can say that for DC voltage without switch, this is not transient, but here DC voltage with switch representing the transient, means one staircase voltage or input voltage. Now for capacitor and for inductor, what happen when we give the input at t equals to 0, it can't follow the sudden change, or it can't show the change across it for capacitor. So that's why you can see just before 0 and just after 0, the values of voltage appearing across capacitor is remain same, and same for the capacitor inductor also. Here you can see that IL 0 minus means current just before switching and or just before 0, t equals to 0, and current just after t equals to 0 flowing through an inductor is remain same. It can't follow that change which is occur at t equals to 0 because of its inherent property. And because of this property, we can see that transient response. Now, here you can see some circuit, and this circuit some contains some, these are called storage element or storage element, or L and C. You can know that they store some energy, they store some charge, you can say charge. So here in this circuit, see only one type of storage elements is here, so we can say the order of this circuit is first order. So order of the circuit is defined by the number of different type of storage elements present in the circuit. Here see this only one type of storage element is present, that's why order is 1. But if you see this one here, both type of two type of storage elements are present, so this order of this circuit is 2. Same here, if you tell this one, if you find out this one is also order of this circuit is 2. But for this one, see, there is no storage element, only resistance is there, and resistance has no effect of transient. So the order of this circuit is zeroth order, as it does not contain any storage element. Now, coming to the today's topic. Today's topic is transient response of RL series circuit. Here I have considered one RL series circuit with one voltage source Vs and one switch. So as we are using this switch, that means that UT term is there. So we are providing one transient input with the amplitude is Vs. And here we are assuming that inductor is initially in relaxed condition. So initially in relaxed condition means inductor does not store any initial current or initial charge. So as we know, inductor always oppose any sudden current change flowing through it. So using this property, now we can see the transient response of RL series circuit. Now say after closing the switch, this is a closed circuit. Now we can simply apply KVL here. So if I apply KVL, so we'll simply write Vs is the amplitude. Because of this switch, we have to multiply with UT. So Vs UT is your source side, and the drop because of R is R into IT and plus L dit by dt. Here we are using I of t or U of t because these voltages are continuously changing with time, varying with time. So that's why IT, these are not constant. Now to find this IT, here IT is the response. So to find IT, what we have to do, see, this equation is not a simple algebraic equation. This is a differential equation. To solve differential equation, here you have to apply Laplace transform approach. You can solve it using classical method also, but it will take time and the method will be lengthy. So it's better to apply Laplace transform approach. After applying Laplace transform, we will get I of s, and then again apply inverse Laplace transform to find IT. So after doing all these steps, you will find this is your IT here. This is your IT. See, IT equals to, we are getting V by R into 1 minus e to the power minus R by L into T. Now say we have to plot it. So say suppose we are putting some values of t. Say initially we are putting t equals to 0. So if I put t equals to 0, so it becomes I of 0. So we will get this is t equals to 0 means this is also 1. 1 minus 1 becomes 0. So I of 0 becomes 0. So now when we want to plot, see initially current is 0. This diagram or this waveform is for current. Okay, so current is 0. Now if I consider at t, the circuit is continuing for a long time, so we say we reach to infinite time. So we can represent t equals to infinity, means its final state. So I of infinity, you can write, if I put t equals to infinity, then you will find I of infinity is V by R, which is the maximum current here. See, so initially current is 0. After that, as there is a e to the power term, so it will follow a exponential graph and then it's reached to its maximum current, which is here V by R, and V by R is a constant voltage. So that means after that means this curve can increase up to V by R, not more than that. So we can say then initially 0 means here inductor basically behave as a open circuit. That is why current is zero, because RL series circuit we are using. So inductor behave as open circuit, so current becomes zero. So at the initial state or the starting state, inductor behave as open circuit. Now as the current progress and reaches to final state, so we are getting maximum current. When we can get maximum current, that if the situation is inductor behave as that time, or in final state, or you can say steady state, at that time behave as a short circuit. That's why maximum current is flowing. So because of this, current initially zero, after that is in the growing format, and then reaches to steady state condition or final state V by R. You can't get more than that. You can maximum get V by R. Now this 1t, 2t all are representing time constant. Here this is the time constant, means if I take 63.2% of the final value, that representing time constant, then we can consider 2 tau, 3 tau, this way 5 tau. Means when we reach 4 tau or 5 tau, we can say we reach to a steady state condition. So this state from 0 to 3 tau or up to 4 tau also you can consider. This condition or this graph is, this time is responsible for the transient response, and after 4 tau now curve reaches to the steady state or final state, means constant value. Now is showing some constant value. Same thing we can do for the voltage also. If I want to find the voltage of across capacitor, inductor, then as we are discussing inductor, so that's why here you have to write V of suffix L, mean voltage drop across inductor. So same way, just you have to put L di by dt. It already we know, so put the it value and then find VLT. VLT equals to L dit by dt. Now it then means do the derivative of it, and then you will get, this is the expression. So for this expression here you can see V into e to the power minus R by L into T. Using the same approach, if you draw it, then you will find this is the graph, and this graph is the decaying graph. Decaying graph, decaying exponential graph. Again it will follow the exponential nature, but in decaying format, because of the same reason that initially inductor behave as open circuit. In open circuit current zero, but you can get maximum voltage, and at the final state inductor behave as short circuit. So for short circuit condition you can get maximum current, but voltage becomes zero. Now after from this these two equation, you can see one term is there, R by L. Okay, so R by L, the reciprocal of R by L is your time constant. Okay, now I will show you what is time constant. So this is an important parameter to analysis of any transient response. So time constant is different for growing curve and for decaying curve. Just now we have seen there are two type of curves we can get. Simple for RL circuit, this is the current curve, this is the voltage curve. Now from any of the curve you can find time constant by using this definition. The definition is, say that it is the time taken for current or voltage graph to reach 63.2% of its final value. This is the reason here 63% is marked and it is written 1 tau. Approximately actual value is 63.2. And for the decaying curve, that it is the time in which the current decays to 36.7% of initial value. Here you have to consider initial value, you can't consider final value because final value reaches to zero. And here always you have to consider final value because initial value is zero. So using these two approach, you can find time constant practically or from the graph. Now time constant, if any, for any system, if time constant is more, say suppose one system time constant is 10 millisecond and another system time constant is 1 millisecond, so obviously the 1 millisecond system response will be higher compared to the 10 millisecond. So we can say the 10 millisecond system is sluggish. Okay, this is the slow system, but the 1 millisecond system is a fast system or rapid system, and always we deserve to have that kind of system where we can get quick response. Now I will show you how the simulation part. The simulation part is this one. See, first we have to, so I am using a multisim.com platform. In that platform, using this, all the components are there from by selecting the components, the required components. So here we need one R, one L. By considering this component, you have to make the circuit first. Simple circuit. See, we are using one step function. Step function you can use from this. Here you will find, say it is written step. From here you can choose step function. Then this from here you can choose ground, and then R1. Some component section is also there. R and L, so you have to choose from here and put the value as per your requirement. Now I have to find the voltage and how much voltage we are giving at the input side, that we can check this probe. This probe is basically working as a voltmeter. Where this probe view, that's of this probe is used as a we have connected this V to measure the voltage drop across the inductor, and this ammeter to measure the current flowing through this circuit. As this is a series circuit, so you can see, you have know that same current will flow. So only one ammeter we have connected in series here. Now, so we already told that we are doing the transient analysis. So means we need UT here, step input. Here some options are given, but we are going to choose transient pattern. Then run it. If I run it, see, three types of waveform are here. One is the blue line. See, this blue line basically representing the input voltage. See, here value is also given. Value is shown 5 volt. Time scale, if you vary, time scale will also vary, but value is 5 volt. Now, in the right side, you can see VL. So VL, now if I now so this is your input and this is your VL. Okay, this green curve representing the voltage drop across inductor. Now if I want to see the current flowing through inductor, this dotted red line representing the current. Now we can choose any one. Either you can choose voltage graph or you can choose current curve for finding the time constant. Now suppose I am choosing the current curve for finding time constant. So I'll remove this voltage curve. Okay, so only you can see one blue line is here that representing the input voltage, and this is your current curve across flowing through the inductor. Now what is the maximum current that we have to find first? How we can find that? We know at final state or steady state, inductor behaves as a short circuit. So here we choose 5 volt and the resistance value is 100 ohm. So V by R is your final value. So V by R 5 divided by 100 means 50 milliampere. So final value current we will get here 50 milliampere. So that's why you can see 150 milliampere current is shown. That is the maximum value or final value. And as we know, the time constant of a growing curve is the 63.2% of final value, which is your 50 milliamps here. So just first we have to find out 63.2% of 50 milliamps. So if you calculate that 63.2% of 50 milliamps, then you will get 31.6 milliampere current. Okay. So now time constant is means time taken to reach 31.6 milliampere. So first, then we have choose to cursor. one C1 cursor and C2 cursor. Now you can move this to both the cursor, you can move, but one cursor we are going to use for reference here. So I am going to set it at the origin. Now other cursor we can move and we will set at 31.6 milliampere value. So how we can set that? See, move this cursor. See here one cursor 2. Cursor 1 is at 0, but cursor 2 is showing, say if this value will change. Now it's showing 36 milliampere, approx 36 milliampere. Now if I vary, see now it's showing 31.7. So if you able to accurately adjust it, then you will get accurate answer or accurate time constant. Now I am getting here 31.7. 31.7. You can zoom it and you can set it at exactly at 31.6. So if you were able to set it at 31.6 milliampere current, then you will find error will be 0. But here where I have set at 31.7 near to 31.6. So in that case, time constant, that time, then means time taken to reach from this value to this value, from 0 to 31.6 milliampere. How much time is taken? So this is your time from 0 to this part is your time representing time. Here cursor to also showing the time. So time is 100.77 microsecond. So 100.77 microsecond is your practical value. Now we have to, as we are doing the simulation or doing some experiments, we have to find the error. So for error, first we have to know what is the theoretical time constant. So in that PPT, I already showed you that theoretical time constant is L by R. So here we'll see L value is we are using 0.01 Henry and R value is your 100 ohm. Now if you divide it L by R, if you take the ratio L by R means 0.01 Henry divided by 100 ohm, then how much we are getting? We are getting uh, 100 microsecond. Okay, but actually in practical, if you say in simulation, after doing simulation, we are getting 100.77 microseconds. So there is a little difference, and using that difference, you have to find out the error. You can consider that 100 microsecond is your theoretical value. So this theoretical minus practical divided by theoretical is your error here. The same thing you can find the same. This is one approach, means you can consider this graph the growing curve or the current curve. Now you can consider the voltage curve also. So now I am removing the current curve. See, you can see only the voltage curve. Now for this, as we want to track the voltage curve only, so here also you have to change the tracking parameter. Now we are using VL is our tracking parameter of voltage. So voltage curve is the decaying curve. Okay, means initially its value is maximum and then it goes to zero, reaches to zero. Finally its value reaches to zero. So initially its value is maximum means final value. So final value you can see this is 5 volt only. And here what you have to do, you have to find 36.7% of initial value. Initial value is 5 and the 36.7% of 5 you have to find first, then again set the cursor C1 at in reference or along y-axis, then move to C2. The C2 curve, if you move, then you will find, see here some value is showing, you have to put at the correct value and then find the time constant. And after finding the time constant, again you will find, you have to find the error. So that error will show you that whether your process is correct or not. So using the split, you can split this to graph also, and at the same time you can see the diagram of the design and this part along with the graph. Now, if can change the value also. If I change the value, see, then now we have choose 0.1 Henry. See, if I choose 1 Henry only, that also possible. From here, choose 1 Henry only, and now you can see the diagram. The diagram is become very flat. That's why you can't see it properly. Now further, if I want to change it, then we can put here 0.01 and 0.1 Henry if I choose, and if I do the transient, see, now we are getting the output form, but still it's flat. Now if I use 0.001, now let's see what type of changes we can observe. 0.001, then see the diagram become very steep. So depending on the L value, we can change the transient response curve nature. Okay, either if I choose this kind of value, say 0.001, see, you can see the value curve is very steep. This curve is not at all suitable for finding the time constant. So your job is, basically here you have to choose the abstract, you have to choose the L value wisely so that you can get a good response curve. If I choose 0.01 Henry, now you can see we are getting a good response curve and we can easily find out the time constant. So after this, I'm ending this session here for today's session. I'm ending this session. Thank you.